Today, we're talking about the architecture of a choice. We usually think of decisions as messy, intuitive things, right? Kind of based on gut feelings. But what if you could actually build a blueprint for any choice, turning these complex problems into a structure that math can solve perfectly? Okay, let's get into it. So, it all boils down to this one question. How can a machine, something that only thinks in numbers, navigate a world of complicated, interconnected decisions to find the single best way forward? Well, the answer is surprisingly elegant. Let's start with a classic puzzle that mathematicians just love. It's called the knapsack problem. So, picture this. You're a treasure hunter, and you've got a backpack with a very strict weight limit. You find yourself in a room filled with all sorts of items, and each one has its own weight and its own value. Your mission is to fill that knapsack to get the absolute maximum value, without the whole thing bursting. It might sound like a game, but this is a perfect model for thousands of high-stakes, real-world decisions. Now, this kind of puzzle belongs to a field with a pretty fancy name: combinatorial optimization. I know, it sounds like a mouthful, but let's break it down. Combinatorial just means we're picking from a huge set of possible combinations, and optimization just means we're hunting for the absolute best one. So all we're really doing is finding the perfect combination that follows all the rules. And this is a huge deal, because it lets us move past just gut feelings and good enough solutions to find a mathematically provable best answer. So, how do we translate a real-world choice like put the item in the bag into the language of math that a computer can actually understand? Well, the entire system is built on one beautifully simple idea. It's called a binary variable. All that means is it's a variable that can only be a 0 or a 1. A 1 means yes or true or on, and a 0 means no, false, or off. Every single complex decision we want to model is going to get broken down into a whole series of these simple yes or no questions. And here's really the best way to think about it. Binary variables are like a massive bank of on-off switches. Each switch controls one tiny little part of the decision. Our job as the architect of this choice is to find the perfect combination of on and off switches to get the best possible outcome. And this is not just some abstract theory. These are the real high-stakes decisions that businesses make every single day. Should we open a new warehouse? That's a 1 or a 0 decision. Should we invest in a huge project? Yes or no? Should this machine run on the night shift? On or off? Every one of these complex choices can be broken down and represented by a simple binary variable. Okay, so we have our on-off switches. Lots of them. But they can't just flip on and off randomly, right? There have to be rules. For example, you can't turn on a light if the main power to the house is off. That's where constraints come in. And this is where the real magic happens. The true power of this whole approach is its ability to translate messy human logic and complicated business rules into clean, precise mathematical inequalities. A statement like, if we open the new warehouse, then we absolutely must hire a manager for it, stops being just a guideline. It becomes a hard mathematical rule that the computer is forced to follow. This slide just brilliantly shows how that translation works. So look at step 1. We start with a simple sentence in plain English. If it rains, then I'll go to the theater. Simple enough. Then in step 2, we turn that into a logical expression. Let's say R is our binary variable for rain and T is for theater. The logic is R implies T. Now for step 3, the really clever part. That logic can be converted directly into a linear inequality that a computer totally gets. T minus R has to be greater than or equal to 0. And just like that, the computer understands the rule perfectly, just through math. So we have our on-off switches, and we have the rules that connect them. What happens when we put them all together? We get something pretty amazing. A literal geometric map of every single possible good decision. This map is called the feasible region. You can think of it as the entire universe of possible answers that don't break any of our rules. Any combination of choices that is valid lives somewhere inside this space. And here's how this map gets drawn. Every single constraint we create acts like a line, basically slicing away all the combinations that are impossible. And as we add more and more rules, they start to form the boundaries of a shape, kind of like a complex crystal. Every single point inside this shape is a valid or feasible solution to our problem. Now here's the crucial part. While our math rules might define this entire blue shape, our actual answers, those simple yes-no decisions, can only exist at these very specific integer points, the red dots you see here. The computer can analyze the continuous blue shape much more easily, and that gives us a really valuable boundary. But the real challenge, the magic of what's called integer programming, is finding the single best red dot within that larger space.
All right, so we have our map of all the possible good choices, but how do we find the single best one? That's the final piece of the architecture.
For that, we need an objective function. This is just a simple mathematical way of stating our goal. Are we trying to maximize profit, minimize travel time, reduce cost? The objective function acts like a compass, guiding us through that feasible region to find the one point, the one combination of yes-no choices that best achieves our goal.
So why does any of this matter? Because this architecture of choice is quietly running the modern world. It's used to manage global supply chains, to create flight schedules for thousands of airline crew members, to design financial portfolios, and even to figure out the most efficient way to cut materials in manufacturing. The scale is just incredible.
So, the next time you face a truly complex decision, remember this structure. It's not just a chaotic mess of options. At its core, it's a set of switches, a series of rules, and a map of possibilities just waiting to be explored. Now that you understand the architecture of a choice, what problems in your own world suddenly start to look a little more solvable?